We've got a new U.S. passenger car. The uncontrolled NOx exhaust emission rate is about 3 grams per mile. The conversion efficiency of a catalytic converter, and it converts NOx back to nitrogen, molecular nitrogen. And we want to meet this emission standard, 0.4 grams per mile. So the question is asking what's the efficiency. Notice that it really doesn't have to be a car in this situation. It's just simply the setting for this problem, which is the conversion efficiency of a catalyst. And simply, like all the other devices that we've been talking about, efficiency is a measure of how much of the material that comes into the device gets removed or converted. And so you look at the inlet and the outlet divided by the inlet here. So here's the solution, very simple. 3 grams per mile minus 0.4 grams per mile divided by 3 grams per mile, and that will be the removal efficiency or conversion efficiency, 86.7%. Closest answer available is 87%. Notice the hint right below that. Mobile source control is not addressed in much detail in the PE exam. Question 29. Determine the stoichiometric air required for combustion of this fuel, octene, which is one of the isomers of that you'll find in gasoline on the compounds. And the answer needs to be given in pounds of air per pound of fuel. It's a mass ratio. Oftentimes in fuel combustion, you're looking for mass ratios, not molar ratios. Okay, so we have to balance the combustion equation for octene. So again, we would start C8H8, and we just simply put down the oxygen because that's the only thing that's actually combusting. And we're going to be forming CO2 and H2O as our products. And very quickly, we can see we're going to get 8 CO2s. We've got 8 hydrogens here. We need a 4 over here, 4 H2Os. We've got 16 oxygens here. 4 more is 20. So we're going to need a 10 right here. Did I say that right? I got the wrong compound. C8H16. So we're going to need 8 H2Os over here. And that's going to come out to 12 oxygens. Okay, so now, at this point, what I like to do is add in the air. Now, air is 79% nitrogen, roughly, and 21% oxygen. If we take that ratio, that's approximately 3.76 molar ratio. And so to this equation, we can add in the nitrogen that is contained in the air very simply by saying we've got C8H16 plus 12O2 plus 12 times 3.76 N2 on the front side of the equation. Back side, right-hand side, we still have 8 carbon dioxides, 8 H2Os. But now all of this nitrogen doesn't participate in the reaction. And notice here in this kind of problem, we ignore incomplete combustion. That is, we're ignoring any carbon monoxide that gets formed, and we ignore fragments, fuel fragments that don't combust at all. So we ignore the VOCs, and we ignore NOx formation. Those pollutants are typically in the ranges of parts per million, maybe up to 1% for CO. But in any case, when we're doing this kind of stoichiometric ratio problem, we assume complete combustion to CO2 and water. So here's our equation. Let me switch over to the typed version. Here's our balanced equation. I started with X oxygen, 3.76 times X nitrogen. Found out because I have 8 CO2s, 8 H2Os, and I'm going to need 12. X is equal to 12, so I put that in. We get 45.1 nitrogen molecules on both sides of the equation. Now, the pounds of air that come in, simply the number of moles of oxygen times the molecular weight, plus the number of moles of nitrogen times its molecular weight, divided by the mass of fuel in this equation, 8 times the molecular weight of carbon, 16 times the molecular weight of hydrogen. And that ratio is 14.7. And you can follow the same procedure for any compound in gasoline that you want to, or that is requested, that you make an estimate of the air-to-fuel ratio for any kind of combustible material. A very simple approach, but it works very well. Okay, let's look at question number 30. Estimate the downwind centerline ground level concentration at a downwind distance, 5,000 meters from the stack, for a non-reactive pollutant, which is emitted from a 90-meter tall stack at a rate of 40 grams per second. You're given the atmospheric stability class and the wind speed at stack height and the plume rise. And this is a simplified form of a Gaussian dispersion problem that you have in the dispersion modeling chapter, chapter 20. In the more complicated cases, you may have to calculate the plume rise. You may have to calculate the wind speed at the stack height by adjusting using the power law. But for this kind of problem in the PE exam, they're not trying to test several different concepts in the same problem. So typically they'll give you that kind of information. All right, so we start with the Gaussian equation. C is equal to Q over 2 pi u sigma y sigma z, e to the minus y squared over 2 sigma y squared, e to the minus z minus capital H squared over 2 sigma z squared, plus e to the minus z plus h squared over 2 sigma z squared. And we notice that for downwind centerline concentration, where y is equal to 0, this term becomes 1. And for z equal to 0, ground level concentration, these two terms are identical and can be factored together. So the equation that we start with in the solution here is C is equal to Q over 2 pi u sigma y sigma z, that remains the same, times 2 exponential minus h squared over 2 sigma z squared. And that's what the equation reduces to when y is equal to 0 and z is equal to 0. Now for class D stability at x equal to 5,000 meters, or 5 kilometers, we can either use the charts in the book to get a quick estimate of sigma y and sigma z as a function of stability class and distance. So we'd find 5 kilometers here, read up to class D, and we have an estimate right there for sigma y. And do the same thing for an estimate of sigma z. Or we can use the equation here with the curve fit equations, where sigma y is a function of x, and sigma z is a function of x, and the values of those curve fit constants are given over here in this table. And since x is greater than 1 kilometer, we have to be sure to use these coefficients for C, D, and F. A and B are for Class D would read across here, and then use C, D, and F for these coefficients here. So given that we can obtain those sigma y and sigma z, if you're reading them off the charts, you probably get sigma y somewhere around 280 to 290, maybe 300 meters, based on just reading the charts. And sigma z probably 90 meters would be your estimate from the chart. These were obtained from the equations, so you get them a little bit more precisely. And then simply plug everything in. There's the wind speed, 5 meters per second. Remember, if that's given to you as a ground level wind speed, you must adjust that up to the effective stack height. And so it would be something greater than 5 at the height. And then simply plugging through the numbers, this gives you the answer, 34 micrograms per cubic meter. Now, the Gaussian equation is widely used. It's the standard for simple dispersion calculations. But as I point out, the box model is widely used as well. And the box model is the basis for calculations if you have a city under an inversion or in a valley. Let's say you have the wind going this way and here's a valley. So like this, trapezoidal shaped valley, and you have a cityscape in there, factories, cars, buildings, etc. And you've got emissions coming in there. So we have the wind blowing this way along the valley. We have an inversion over there that limits the mixing height. And we can do a very simple box model where the wind velocity times the front area of that box times the inlet concentration, which may be 0 or may not be, the inlet concentration of the pollutant, would be equal to whatever emissions occur inside the box plus the amount of material being carried out, U times A times C exit. We put the C in, C out, so there's no doubt. And if you don't know the outlet concentration, you can easily calculate it this way. This is the steady state box model. Even if you don't have a valley, you can do the same thing by imagining a box around the city with the limited height by the inversion. And the front face area is simply the width times the height of the inversion. Well, that same equation, that same principle is used in calculating an indoor air concentration and solving an indoor air problem. And of course, the concentration inside the box or inside the room, as it were, here is by nature of solving it as a box model, it becomes a single number. That is, you're not able to discern any gradation of concentrations or any dispersion of the pollutant. It's assumed to be uniformly mixed throughout the volume of the room. So we come out with one number. And you can't say it's any higher near the beginning or near the end with the box model. So the Gaussian model gives you the ability to discern concentration gradients both in the horizontal width and in the vertical height. Box model is a simple, completely mixed tank, if you were, a completely mixed box. So you have one concentration. So here in problem 31, we have a fireplace in a room. It's releasing NOx at the rate of 5 milligrams per minute. Given the dimensions of the room and the ventilation rate of the room, 1 air change per hour, and the inlet concentration of the fresh air, NOx concentration is 0. Estimate the steady state concentration of NOx in the room. So steady state, of course, implies that the fire is burning at a constant rate, it's releasing NOx at a constant rate. We've had enough length of time where the fire is burning so that we've reached a point where the concentration in the room is no longer changing, either accumulating or dropping. And we're going to ignore any chemical reactions that might occur within the room. Now, the only tricky thing about this is the air change. To get the air change, we need the volume of the room. And since we have the dimensions, we get the volume of the room as being 60 cubic meters. And 1 air change per hour means you get 1 volume of room changed every hour. So a volumetric flow rate is 60 cubic meters per hour. At steady state, we have 0 accumulation. Our input, air coming in with a 0 concentration, plus the input from the fireplace, 5 milligrams per minute, converted to micrograms per hour here to keep up with our units of time. So milligrams per minute times 60 minutes per hour times 1,000 micrograms per milligram. These are the 2 inputs to the room, one of them being 0, minus the output times the output concentration C, and we can solve that simply for C equal to 5,000 micrograms per cubic meter. Okay, so that completes the PE review problems. And I'm going to take a short break here, and then we'll come back and see what else we've got to do. I wanted to thank you for sticking with me this long and through 31 of those PE problems. And as a reward, I'll give you 2 answers to problems at the ends of the chapter. And in fact, not only the answers, but the method of solution. So, or whatever that's worth. You may already have these anyway. First one is problem 10.4 in your text. And 10.4 says, calculate the partial pressure and gas